this video, we're going to look at a second type of multiplication of vectors, and this is what's often called the cross product, because we use an X symbol as opposed to dot product, in which we use a dot symbol. It's also called the vector product because the result of this multiplication is a new vector. So in the scalar product or dot product, when we multiply the two vectors together, we get a scalar, a numerical value. Here we are actually going to get a vector resulting from this multiplication. So if we have two three-dimensional vectors, we can't really do this with two-dimensional vectors. If you have two-dimensional vectors, you have to make the third component be a zero so that they are three-dimensional vectors. And this will produce a new vector. And it does need to be in three-dimensional space because what the property that this new vector is going to have that's special, that's helpful, that makes this a useful product, is that the vector that is produced will be perpendicular to the original two vectors. So the original two vectors can form a plane potentially, and then we get a new vector that's perpendicular to them both. So the cross product is given by this formula here. It's not necessarily a super intuitive formula. If we had time for a full exploration of matrices, what we would see is that this is comparable to the determinant of a 3x3 matrix, but that's beyond the scope of this course. So we have this formula. It's in your formula booklet for your IB exams. You can try to memorize it, feel free. But essentially the idea is it's a combination of the various components in this sort of complicated way. So looking at it with actual numbers makes it a little clearer to understand. I'm actually going to express these as vertical column vectors because I find that makes it easier for me to organize them. So if I have this A vector, which is 2, -1, 4, as a cross product with the B vector, which is 1, 3, -7. For the first component, I'm going to take the second component of the first vector, so that's -1, times the third component of the second vector, so -7, minus, now the other way around, the third component of the first vector and the second component of the third vector. So essentially what I'm doing for this first component is I'm not using the first components, I'm multiplying the -1 and the -7 and subtracting the 3 and the 4. So that's how this first component is going to be determined. For the second component, I'm ignoring the second components and I'm going to multiply the first and thirds, but notice that the subtraction gets done in the opposite order. So I start with the third component of the first vector, so 4, times the first component of the second vector, so 1, and then I subtract first component times third component. And then finally, when I am doing the third component, I ignore the third component, and so what we're going to do in this one is first times second minus second times first. So it's not completely random and arbitrary how that formula came about. So I have 2 times 3 minus -1 times 1, which means that when I do the cross product of A with B in this order, I get 7 minus 12, so -5. I get 4 plus 14, so 18. And I get 6 plus 1, so 7. This is the resultant A crossed with B. Now I claimed that these were perpendicular. We can verify that by checking a dot product. I'm just going to check that it's perpendicular with A. So if I have 2, -1, 4, and I do the dot product with -5, 18, 7, well, 2 times -5 is -10, plus -1 times 18 is -18, plus 4 times 7 is 28, which is in fact 0. So these are perpendicular. And the same would result if I did the dot product of this new vector with B. It would be perpendicular to B as well. But what I want us to actually do is verify this in the opposite order, because this is a pretty complex formula and we can't always assume that operations are going to be commutative. So if I do this in the opposite order, so in other words, if my first vector is now 1, 3, -7, and the second vector is 2, -1, 4, then the multiplication and subtractions are going in a different order. So I do for the first component, remember I'm looking at the second and the third. So 3 times 4 is 12 minus negative 7 times negative 1 is 7. And when I'm doing the second component, I go negative 7 times 2, which is negative 14, and 1 times 4, so negative 14 minus 4. And for the third component, 1 times negative 1 minus 3 times 2. So we end up in this case with 5, negative 18, negative 7. So not the same vector. A parallel vector, it's the opposite vector, but because everything has been done in the other order, this particular operation, cross product, is not commutative. So the order is important. Either way, it does produce a vector that is perpendicular to the two original vectors, which means that the two vectors that are produced by doing the cross product in the opposite order have to be parallel to each other, and they are in fact just opposites of each other. So there is an alternate formula here for the cross product, which is that the cross product of A and B is the magnitude of A times the magnitude of B times the sine of theta. So all of that's going to give us a numerical value times a vector here. It's a unit vector u, where theta is the angle between A and B, and unit vector u is a unit vector that's perpendicular to both A and B. Now, this doesn't end up being super practical in everyday life because finding a vector that is perpendicular to the two original vectors is tricky. That's, in fact, the most common reason we would use the cross product is we are trying to find a vector perpendicular to the other two. And so normally I would use the cross product first and then divide out by its magnitude. But the key point here is that this does tell me what its magnitude is. The magnitude of that cross product is the magnitude of A times the magnitude of B times the sine of the angle between those two vectors. So if those two vectors are defining two non-parallel sides of a parallelogram, so let's say I have a parallelogram that goes like this, in which, oops, that's not especially parallel, but you get the idea. If this is a vector A, let's say for this side, and then I have a vector B for this side, then the cross product, and so I'd have theta here, the cross product is actually going to be equal to the area, well, the magnitude of the cross product, because the cross product itself is a vector. The magnitude of the cross product is the area of that parallelogram. And we've seen something similar to that in that half of that parallelogram is a triangle, and that means that half of the magnitude of the cross product is the area of that triangle. So we can use this result in that way.